Hey, Vsauce, Michael here, and my tea is quite hot, but it's not the hottest thing in the universe. So what is? I mean, we know that there is an absolute zero, but is there an absolute hot? A point at which something is so hot it can't get any hotter? Well, to find out, let's begin with the human body. Your internal temperature is not constant. 37 degrees, 98.6, sure, but those are averages. Your body's internal temperature fluctuates by about 1 degree Fahrenheit, half a degree Celsius, throughout the day in a cycle. Assuming you sleep at night, at 4:30 in the morning, your body reaches its coolest, natural, healthy temperature, and at 7 p.m., it reaches its highest. But a dangerous fever is not good. 108 degrees Fahrenheit is almost always lethal. The highest recorded air temperature across all of Earth has happened 4 times in Death Valley, where it has reached 129 degrees Fahrenheit. 180 degrees Fahrenheit is the recommended temperature for water when brewing coffee, and at 210 degrees Fahrenheit, a cake is done. 2,000 degrees Fahrenheit is the temperature of lava fresh out of the ground. But come on, make your own lava like Green Science Pro. This guy uses Fresnel lenses to focus the sun's energy onto whatever he wants. This is a small piece of obsidian, volcanic glass, which he can melt into actual lava right in his backyard. Keep in mind that the sun is having that effect even though it is 93 million miles away from Earth. Right up on the surface of the sun is a different story. The surface clocks in at 10,000 degrees Fahrenheit, but the center, where fusion occurs, is ridiculous. Temperatures there reach 28 million degrees Fahrenheit, which is also known as 15 million Kelvin. The Kelvin scale has units that are the same size as a Celsius degree, but it's an absolute scale, where 0 is absolute zero. When matter reaches temperatures as high as those found in the center of the sun, an enormous amount of energy is radiated away. If you were to heat only the head of a pin to the temperature of the center of the sun, it would kill any person within 1,000 miles of it. Speaking of which, the energy emitted by an object often tells us a lot about the temperature of that object. Any object over absolute zero emits some form of electromagnetic radiation. You and me, we don't glow visibly, but we do emit infrared light. We can't see it, but infrared cameras can. WBD has great videos, and here he is hiding inside an opaque black trash bag. Now, we can't see him, but his body is infraredly glowing through it. If you want something to be the right temperature to glow in the visible spectrum, you'll have to reach the Draper point, about 798 Kelvin. At this point, almost any object will begin to glow a dim red. We can calculate the expected wavelength of radiation coming off of an object because of its temperature, and that wavelength gets smaller and smaller the hotter and hotter the object gets. It goes from radio waves to microwaves up through infrared to visible, all the way to X-rays and gamma rays, which are created in the middle of our sun. At temperatures as hot as the sun, matter exists in a fourth state. Not solid, not liquid, not gas, but instead a state where the electrons wander away from the nuclei. Plasma. If you've watched my temperature lean back, you know that you can make plasma by microwaving fire. But don't do it. Besides, our sun isn't even close to being the hottest thing in the universe. I mean, sure, 15 million Kelvin is pretty incredible, but the peak temperature reached during a thermonuclear explosion is 350 million Kelvin, which hardly counts because the temperature is achieved so briefly. But inside the core of a star, 8 times larger than our sun, on the last day of its life, as it collapses in on itself, you would reach a temperature of 3 billion Kelvin. Or if you want to be cool, 3 gigakelvin. But let's get hotter. At 1 terakelvin, things get weird. Remember that plasma we were talking about that the sun is made of? Well, at 1 terakelvin, the electrons aren't the only thing that wander away. The hadrons themselves, the protons and neutrons in the nucleus, melt into quarks and gluons, a sort of soup. But how hot is a terakelvin? Frighteningly hot. There's a star named WR104, about 8,000 light years away from us. Its mass is the equivalent of 25 of our suns. And when it dies, when it collapses, its internal temperature will be so great that the energy emitted, the gamma radiation it flings out into space, will be stronger than the entire amount of energy our sun will ever create in its entire lifetime. Gamma ray bursts are quite narrow, so Earth is most likely safe. But what if it wasn't? Well, when WR104 collapses, even though Earth is 4,702 trillion miles away, the energy it releases would still be bad news. Exposure for 10 seconds would mean losing a quarter of Earth's ozone layer, resulting in mass extinction, food chain depletion, and starvation. From 8,000 light years away. Closer to home, right here on Earth in Switzerland, scientists have been able to smash protons into nuclei, resulting in temperatures much larger than 1 terakelvin. They've been able to reach the 2 to 13 exakelvin range. But we are okay because those temperatures last for an incredibly brief moment and only involve a small number of particles. Remember how we could calculate the wavelength of the radiation emitted by an object based on its temperature? Well, if an object were to reach a temperature of 1.41 times 10 to the 32 Kelvin, the radiation it would emit would have a wavelength of 1.616 times 10 to the negative 26th nanometers, which is tiny. Like, so tiny it actually has a special name. It is the Planck distance, which according to quantum mechanics is the shortest distance possible in our universe. Okay, well, what if we added even more energy? Wouldn't the wavelength get smaller? It's supposed to, but yet it can't. This is where we've got a problem. Above 1.41 times 10 to the 32 Kelvin, the Planck temperature, our theories don't work. The object would become hotter than temperature. It would be so hot that what it is would not be considered a temperature. Theoretically, there is no limit to the amount of energy we could keep adding into the system. We just don't know what would happen if it got hotter than the Planck temperature. Classically, you could argue that much energy in one place would instantly cause a black hole to form. And a black hole formed from energy has a special name, a Kugelblitz. So basically what I'm trying to say is when you want to tell someone you like that you think they are hot, so hot that not even science can understand it, just call them a Kugelblitz. Finally, here is something fun. The sun is about 4.7 billion years old, about halfway through its life cycle. And so far, it has burned 100 Earths worth of fuel. Which sounds like a lot, but the sun is the size of 300,000 Earths. Because of that discrepancy, you can have a lot of mathematical fun comparing your energy output to the sun's. The sun is way hotter than us, and it puts out way more energy than us. Bad Astronomy had a lot of fun with this one, and although it doesn't really mean anything, it is technically true, because of the sun's enormous size, that 1 cubic centimeter of human puts out more energy than an average cubic centimeter of the sun. Which should make you feel quite warm inside.
И, как всегда, спасибо, что смотрели.